As we left the last video, we were confuddled because we wanted to use this equation, work equals negative P delta V, to describe the amount of work done by the pistons on this gas. However, we realized that the pressure, as we drop this cylinder down, is increasing. Let's get an idea of how we can resolve that situation by imagining a pressure versus volume diagram. And we'll start here at a certain pressure and a certain volume. Let's actually put that line up here. Okay. And then we decrease the volume. No, we're decreasing the volume, right. So we'll start over here at a certain pressure and a certain volume. And we're decreasing the volume and the pressure goes up. And then we decrease the volume a little bit more and the pressure goes up a little bit more. We decrease the volume a little bit more and the pressure goes up a little bit more. So you can imagine that the pressure keeps increasing as we decrease the volume. And this isn't just a line, it's a directed line. It has a path direction as you go around to say which direction we're changing things by pushing the volume smaller and increasing the pressure. So you can imagine during each of these phases of decreasing volume, you could say that the pressure is relatively constant during each phase. And so the work done during this phase is going to be this pressure times this change in volume, and the work done during this phase is this pressure times this change in volume. And so you can just add up the sum of all of those pressures. Each pressure is different at each volume, so pressure P of V times delta V, or you can write it in integral notation, integral of P dV, where P is a function of V. Forgot my negative sign. Negative P of V delta V and negative P dV. Now what I'm showing you there is called a PV diagram. A PV diagram is used when the pressure and volume are known at each step in the process. The work done on a gas that takes it from some initial state to some final state is equal in magnitude to the area under the curve on the PV diagram. So in this case where you have a constant pressure, you still use that P times delta V. This is the delta V here, and since it's going that way, this is a negative number. In this case, the P delta V, or negative P delta V, is going to be the same whether you use the equation or the diagram, because it's a rectangular shape. But this case where the work is equal to the area under the curve is true whether or not this pressure stays constant. So let's look at some other examples. Here's a case where the pressure and volume are both increasing. What could cause that kind of phenomenon? Well, in general, as the volume increases, the pressure goes down. In order to get this to happen, you would need quite a temperature increase to create an increasing pressure even as the volume was growing. In this case, you have a sudden drop in pressure followed by a shrinkage, followed by another sudden drop in pressure, followed by another sudden shrinkage. In this case, you've got an increase of volume from 1 cubic meter to 2 cubic meters, followed by, or I should say without any change in pressure, followed by this same strange situation we had over here where both the volume and the pressure were increasing, probably by a big increase in heat. And here we have a decrease in volume followed by a big drop in pressure followed by another decrease in volume. The curve on the diagram is called the path taken between the initial and final states, and you'll notice it does have a little arrow on it, so this is clearly marked as initial state and final state. the work done depends on the particular path. First of all, the area under the curve tells us the magnitude of the work, and then the direction, whether it's going to the right or left, tells us whether the work is done by the gas or whether the work is done by the environment. Or more notationally correct, whether the work is done on the gas or whether the work is done on the environment. In this case, the gas is doing the work. The gas is doing the work, therefore work is going to be negative. The W, because this is the work done on the gas, is going to be negative. In this case, the work is done, actually, let me write down work ENV is going to be positive here, because the work done by the gas on the environment is positive here. In this case, the work done on the environment is going to be negative, and the work done on the gas is positive. Because the gas is shrinking, you're doing work on the gas to shrink it, to squeeze it. Likewise, this one's going to the right, so the work on the environment is going to be negative, is going to be positive, and the work is negative. Remember, W is the notation for the work done on the gas. Let me go ahead and show you what the PV diagram for an adiabatic expansion actually looks like. Recall I drew this stair-step design where each time I decreased the volume, the pressure increased. Now, an actual PV diagram isn't going, for an adiabatic expansion, isn't going to have a stair-step design. It's going to look more like a curve. This is a adiabatic expansion. The adiabatic compression would look basically the same, except the arrow would be pointed in the opposite direction. In particular, you'll see that the governing equation behind this is that PV to the gamma equals constant. And so let's just call that constant K for now, and we'll see that this P equals KV to the negative gamma, because just divide by V to the gamma. Gamma is given as C sub P over C sub V. Yes, it's known as the adiabatic index of the gas, and it has to do with the specific heat of the gas, the molar specific heat of the gas at constant pressure divided by the molar specific heat of the gas at constant volume. Now we'll go into that pretty soon, but for now just realize that it's going to probably be a number like 5/3 or 7/5, depending on the type of gas it is. I think this is for a monatomic gas and this is for a diatomic gas, for instance. Anyway, that equation P equals KV to the negative gamma is going to give you some line like this, and then if you take the area under that curve, that will tell you the amount of work done by the gas as it expands or contracts adiabatically. Hopefully in the next couple of videos I'll be able to explain exactly what the specific heat at constant pressure is and the specific heat at constant volume is, and why in particular this equation pops out of the ideal gas law and certain assumptions about the behavior of pressure, volume, and temperature when no heat can be exchanged. That is, when no heat can enter or leave the gas. Now I think that in order to explain the adiabatic expansion and work, or the relationship between pressure and volume and work in an adiabatic expansion, we would need to go back to chapter 10 to recall the information about the monatomic gas bouncing around in a cube. In particular, we want to focus on why this number was 3/2 and how that would change if we had, instead of a monatomic gas in here, if we had a diatomic gas or some other more complex molecule. And how this thought experiment of having the particles in the box would change depending on whether we decided to have a constant pressure or constant volume, or neither.